Hi, BC people. So I hope this is Monday and you have this handout for you. We're going to continue off our lesson from last Wednesday, differential equations. This will be a little bit more that you need to know. Take about 25 minutes and then you'll have the rest of the period to work on the homework. You should have checked Google Classroom for your answers to the 87 fun sheet and hopefully turn that into the basket by the end of the day. All right, so here we go. Pause the video if you need to. If I go too fast, I have a hard time getting a feel for too fast or too slow when I'm by myself. All right, check it out. So there are three really famous differential equations that any Calc 1 and 2 student should know. We'll cover two of them today, and the third one we'll cover set 115. All right, so here goes. First is the huge differential equation, y prime is ky. So what? Why is that important? Well, here we go. Let me introduce you with a money idea. Say Joe starts with $10 and earns 10% simple interest every year. Joe would then start at $10. He earns 10% of $10, so he earns $1. But because it's simple interest, it's going to always be $1. Despite the fact that after the first year he's got $11, he doesn't get earned interest on that. He ends year 2 with $12 and ends year 3 with $13. Joe's money therefore changes at a constant rate. Every year that passes, it's going to go up 1 over 1, up 1 over 1. It's linear, yeah? Now if I were to treat that in a differential equation kind of way, I would say that the rate of change in Joe's money is constant. A for constant. If I solve that equation, I could separate the variables, most important step, integrate both sides, and I'd get the amount as kt plus a constant. I know that at time equals 0, a equals 10, so that would imply that c is 10, and therefore my equation is complete, kt plus 10. In other words, linear. Totally logical, yeah? Better, though, is the exponential side. Lou gets compounded. So first year is 10% of 10, which is $1. So far the same. But in the second year, Lou will get 10% of 11, which is 1.1. And so after year 1, after year 2, Lou will have $12.10. Now, the amount in the account is $12.10 at the start of year 3, 3. And so 10% of 12.1 is 1.21. If I add $1.21 to the previous balance, I get $13.21. If you were to analyze that, it would tell you that you made 21 cents of interest on interest. Now all that's great, but this is the calculus step. Lou's money changes at a rate that's proportional to the amount. The rate of change, you could say, could depend on two things. It's logical to say, well, the rate of change depends on time. But really, the rate of change is more directly related to how much is in the account. How it's changing depends most directly on how much is in the account. So rather than dA dt being a function of time, it's more common to say dA dt is a function of the amount. Now let's talk about that. If I say what makes that different, then that means the rate of change depends, the rate of change on the amount depends on the amount. That's pretty weird that the derivative depends on the dependent variable, but it happens in this case. Now this is a really famous statement. Your eyes should light up and twinkle when you hear this in the future, because it's a big deal. If I were to take this and put it into calculus, amount grows at a rate. That means dA dt. That rate is proportional to, so think constant of proportionality times the amount itself. The rate at which the amount grows relates to the amount itself. Now I'm going to actually move over here because I might need a second column here. I'm going to work down as always. Let's go from this. If I separate the variables, then that would mean dA over A equals K dt. And if I then integrate, natural log of A, absolute value of A, equals K T plus C. Now let's assume A is positive in this case. So the absolute value of A can just be written as A. So I'm going to call this natural log of A equals KT plus C. If I use the initial condition, and it's kind of a general universal initial condition I'm going to use. At time equals 0, the amount is equal to the initial amount. Then I get natural log of A initial equals 0 plus C. That implies that C is the natural log of A initial. If I put in that C, then I get the natural log of A equals KT plus the natural log of A initial. Solving for A yields A is e to the, now when I exponentiate, be careful here, algebra time. When I exponentiate, obviously on the left it's exponentiate. On the right, is it exponentiate here, E there, E everywhere? Or is it E to the whole side? And I hope you're saying it's E to the whole side, not E to each. It's like if I added 2 to each side, I wouldn't add 2 to every little thing I saw. I would add 2 to one side, to the whole side. That's it. Okay? Now, using a little bit of exponent rules, I know that x to the a plus b could be split into x to the a times x to the b, all right? And that means that right side, right, could be changed to e to the kt times e to the log of a initial. And that simplifies to a initial, e to the kt. And so the idea of that statement and the differential equation that goes with it, that's where exponential growth comes from. You learn exponential growth first because you can't understand calculus in Algebra 2, but that's where it flows. All right. Okay. So the idea of proportional relates to this really famous differential equation. Now sometimes instead of dA dt, they call it y prime and relates to y itself. But the idea is when you see a differential equation that relates to the independent variable, or the dependent variable, then think exponential growth first thing. It'll save you some time on problems like this. Check it out. So temperature changes according to the differential equation, dF dt equals kF. And the first thing that should cause you to light up is, oh, rate of change of f depends on f. That means exponential growth. And so right away I think this. All right, so at time 0, k equals 180. At time t, 16, f equals 120. What does kf to be? Well, now that I have this, I know exactly what's going on. The initial is 180. And this case could be put in to find k. 120 equals 180 e to the 16 K. If I solve that for K, I would divide by 180, natural log, and divide by 16. So I get the log of 12/18 divided by 16. Boom. Whatever that is, that's the answer you'll see. All right? Now I want you to then be able to easily flow from differential equation to solution equation. So that's what this is practicing, trying to go from one form to the other. So given two of the three parts, you should be able to find the third. Take 30 seconds to do this. Okay, so given that this is obviously exponential growth, I know that this is A, so T equals A naught e to the KT. I just need to figure out what's A naught and K. A naught is 200, that's given here. K is 0.03, that's given there. T stays varying, there's my equation, okay? This way, I need to first of all say what variables. In this case, it's y and t. So dy dt, or if you like y prime, I suppose, but I like dy dt better, is ky. In this case, k can be found here. K is 3. So dy dt is 3y. The 42 didn't really get used. And then finally, if I want the initial of p initial, can be found in the equation in front of the exponential change component, 1,300. Easy enough? Good. All right. Switch to the back. A second very famous law of differentials is Newton's law of cooling, or heating, I suppose, depending on how you look at it. The idea is something like this. If you say you pulled a pizza out of the oven that was 400 degrees, now when the pizza was in the oven at 400 degrees, the pizza itself was 400 degrees. But when you pull that pizza out of the oven and put it on the counter, then it starts to cool. How fast it cools depends on a few things. First of all, the nature of the pizza, the material itself. That has to do with how fast it cools. The temperature of the pizza when you pull it out, that goes into how fast it's cooling. And then finally, how cold or hot is the room. That affects the rate at which something cools. The three components then are these. The rate of change in the temperature of the body, in this case the pizza, depends on K, which has to do with the material itself that's cooling. And the difference between the pizza and the room. T sub B is the temperature of the body. And yes, you can actually use this idea for avidity, things like that if you like crime scene kind of TV shows. And the difference in the room. Altogether then, this is the rate of change in the body, but it's not the temperature of the body. In this case, it's easier to start with how is the temperature changing, what goes into that, than to just go to the body temperature. We actually need to work up to that. Before we get that, I like to do this better. Rather than T sub B and T sub A, I just like to use B for the temperature of the body and R for the temperature of the room instead of ambient temperature. All these T's tends to kook me out. So I'm going to rephrase this as The change in the body temperature relates to the difference between the body temperature and the room temperature. Now, if you prefer to use the T's, so be it. Okay. If the body is warmer than the room, is d body dt positive or negative? Well, if the body's warmer than the room, then when it's placed in the room, the body will cool. And so the rate of change in the body temperature will be negative. Now, if the BDT equals K times body minus room, if dBdt is negative, and the body minus the room. Now, if the body's warmer than the room, then body minus room will be positive. In this case, then, K should come out to be a negative. What about if the body's cooler than the room? I'm again going to rephrase this as dBdt. Now, if the body's cooler than the room, the body will raise in temperature towards the room's temperature. So dBdt is going to be positive. If dBdt is K times the body minus the room, and we say dBdt is positive, what about B minus R? B is cooler than the room. And so the body temperature is less than the room. And so body minus room is negative. It seems like in both cases, K is negative. So you can expect negative K when you do these problems. Now, all that said, back to the question. Great, you've got this, how it changes. But what about the temperature of the body? Let's do this case. Say an object is pulled from a 300-degree oven and placed into a 70-degree room. After 10 minutes, the object has a temperature of 200 degrees. Find an equation for temperature. Now let's start with the differential equation. The differential equation is dB dt is K body minus room. Now, we can plug one thing in right away. The room temperature doesn't change. Yeah, I know, you're probably saying, well, you know, if you put the pizza into the room, it might affect the temperature. Let's assume the room's temperature doesn't change. So let's put it in, because it's not varying for this problem anymore. We know is 7. Now we get towards solving. K we don't know, and B does change, so we have to let the rest stay varied. Now we need to separate the variables. dB over B minus 70, they have to be kept together. And K dt, that's how you would separate the variables there. B minus 70 gets divided over. K is easiest to keep on the right. If I integrate, then I get the natural log of the absolute value of B minus 70 equals KT plus a constant. You follow? All right, now let's use the initial condition. First initial condition. At time equals 0, the temperature of the body was 300. When it was pulled out of the oven, it was 300 degrees. So that's the natural log of 300 minus 70 equals 0 plus C. We can see that C is log of 230. Now we write our equation with C in. The log of the absolute value of B minus 70 equals KT plus log of 230. Now, we could use the second condition, plug in the next condition to find K. We know that at time 10, the temperature is 200. Log of 200 minus 70 equals 10K plus log of 230. That's a little bit gross, but we'll work it out. This is log of 130 minus log of 230 divided by 10, yay? But by log rules, it's more common that you'd see log of 130 over 230, or 13 over 23 divided by 10. Cool? All right, now we're going to solve for b. If log of the absolute value of b minus 70 equals log of 12/13 over 10 t plus log of 230, then I could exponentiate. And when I exponentiate, it's e to the all of it, yeah? E to the log of 12/13 over 10t plus log of 230. We talked a second ago how this can be split up into a product. And then you have inverses that cancel. So b minus 70 is plus, or, oops, not plus or minus yet, 230, if I put that in front, e to the natural log of 12/13 t over 10. T is not in the argument. Sorry about that. Right? If we dump the absolute value next, it's plus or minus 230 e to the log of 12/13 over 10t. And so b is 70 plus or minus 230 e to the log of 12/13 over 10t. Now we have to choose. If b equals 300 at time equals 0, then we need to use the positive. b equals 70 plus 230e to the log of 12/13 over 10. Now sometimes rather than solve for k here, some books will solve for k later. I think in retrospect, I think that would have been less writing because that clunky carrying around that. I think the best thing would have been to just say, you know what, I found k, I'll plug it in later, and just kept calling this k the whole time, so I didn't have to write that the whole time, and only at the very end plug in k. It would have been the easiest way to do that. So in the future, I would encourage you to, after finding k, just keep calling it k, and at the end, bring it back. Okay? Okay. Next idea. Switching gears. Verifying a solution. Remember, when I say a solution in an algebra equation is one that makes the equation true. So for example, if I said verify x equals 2 as a solution to this, and I could plug my solution in to the equation again. And I get 3 times 2 minus 4 equals 2 is true. Yeah? Now verifying a differential equation solution is a little more complicated. I am going to use, the question is usually students will say, well, what plugs into what? You get all confused. So let's be very clear. We're going to use this to plug in to this and show this is true. Now I want to plug everything in here that it calls for in. So the first thing I'm going to need is to get y prime. If y is 3e to the 2x, then y prime is 6e to the 2x, yeah? Now I'm going to plug in to the differential equation. Y prime gets replaced by 6e to the 2x. Y gets replaced by 3e to the 2x. And hopefully you should get something that is obviously true. Anybody that knows a little bit of Algebra 1 knows that that is true. Yay? Okay, let's try one where you'll have to do a little more. Verify this solves this differential equation. Now this has the second derivative, so we're going to need y prime and y double to plug in. So we're going to start there. Y prime is, product rule. First stays the same. Derivative of the second would be e times 2 cosine of 2x plus second stays the same, derivative of the first. See? So we clean it up. Before we take the second derivative, what do you think? I think I will. I'm going to say e to the x times 2 cosine of 2x plus sine of 2x. Y double then, by product rule, is first stays the same. Derivative of the second is negative 4 sine of 2x plus 2 cosine of 2x. Plus second stays the same, 2 cosine of 2x plus sine of 2x times derivative of the first, e to the x, yeah? Now based on that, I can see that if I take y double minus 2y prime plus 5y and say that's supposed to equal 0, then in place of y double, I could say something like e to the x times negative 4 sine of 2x plus 2 cosine of 2x. Oh my. All of that plus 2 cosine of 2x plus sine of 2x, all of that times e to the x. That's y double. Negative 2y prime is negative 2 e to the x 2 cosine of 2x plus sine of 2x plus 5y. Phew. Bet you wish you could do this. Plus 5y is plus 5 times e to the x sine of 2x. All that's supposed to equal 0. My goodness. So if I distribute here, let's look at all the ones that will be sine e. I'm going to have negative 4 e to the x sine of 2x there, and plus 1 e to the x sine of 2x there, and then negative 2 e to the x sine of 2x there, and positive 5 e to the x sine of 2x there. Altogether, I got positive 5, positive 1, that's 6, minus 4, minus 2, that's negative 6. The signs all go away. The cosines, I'd have 2 e to the x cosine of 2x. I'd have positive 2 e to the x cosine of 2x there, and negative 4, e to the x cosine of 2x there, and surely those equal 0. And so I get, now that's as ugly as you're going to get. Second derivative is pretty gross, and that's products rule also. It's pretty clever. But now you've seen the worst that you're going to see. All right? That should do it. The ones on the homework are a little more straightforward. So would you get out set 88 part 2? It's got 2 pages to it. And it's actually not too bad. You have the rest of the period to work on it, and we will go over it on Tuesday. Have a good day.